Thank you. Okay, so I'm gonna unmute you, Galaxy A30s. Okay, thank you. Okay, so we can start the session. Can you see the document that's on the sharing board?
Yes.
Yes, engineering. One. Okay, so let's start. Let's look at question number 1. Question number 1 goes like this. The force acting on a particle varies as shown in figure 1. Find the work done by the force on the particle as it moves from position x is equal to 0 to x is equal to 8, isn't it? So this is the area above the graph. If you look at the diagram, figure 1 here. So the area above the x-axis. Understand? Okay. The area under a force distance graph gives us work. So I hope you know that. Okay, from the definition of work is the product of the force times distance traveled by that force, isn't it? Or the distance parallel to the force. Is that right? Okay, thank you. So in this case, there's the graph of force against distance. So to find the area under the graph, remember you're multiplying the two entities, the x and the y. You understand? So in this case, we can be able to find, okay, Koza, you raise your hand. Let me just attend to you just now. What's the problem? Koza. Hello, Koza. Okay, he's not saying anything. Let's continue. Okay, so the area under the cave, it gives us the product of these two entities. So in this case, we are looking for what is the work done by the force when it moves from x is equals to 0 to x is equals to 8, which means from this point to this point. So in this case, it's just the area under the cave. So we can calculate area under the cave using metric maths. You know, area under a triangle, it's given by half base times height, isn't it?
Yes.
Okay. So in this case, our half times the best we can take it as 8, right?
8. 8, yes.
Times our height, which is 6. $24. We also getting 24.
Yes.
Okay, sure.
24.
Okay. Now this is part A. Let's go on to part B. What is part B saying? Part B is wants us to calculate the work done from a distance x is equal to 8 meters to a distance where x is equal to 10 meters. So this is the area under this cave. Can we just use a different color here so that it may be clear for you guys? I'm gonna use, okay, let me use, I'm gonna use blue, okay? So this is the area that we're looking for now because it's from 8 to 10, isn't it? Actually, it's not the whole area because you see where, just wait a second here. Okay, so it's from 8 to 10, right? So
yes.
The area ends here with a stain here. So it's this side. Okay. So now let's find that area. Again, we use the same principle. Half base times height. So it will give us, what is our base? In this case, I'm gonna use the difference between 10 and 8 as well,
8.
which is 2, right?
Mm.
Hmm?
Yes.
Our height is from this point to that point. So
3.
each division represents 1, right? So this is 1,
Yes.
2, 3, 4. So this is -1, -2, -3. So the height is -3, isn't it? Okay. So what do we get here?
-3.
Okay, -3.
Then divided by 2.
-3. Oh, remember we need to put the units here because this is energy. What are the units of energy? It can be Newton meter or joules. Okay.
Joules.
So here it's also joules. Okay.
But isn't
Sorry?
8 to 10? Okay, yes.
Yeah.
Sorry.
You get it?
Yes.
Exactly. Okay. Anyone with a problem, you just raise your hand. I'll attend to you. Okay. Let's continue. Now from point where x is 0 to a point where x is equal to 10, isn't it? Let's calculate the total energy. So it's just we just add these two, isn't it?
No.
Why are you saying no?
It's 10, yes.
Sorry?
Okay, I get it now. I get it.
Yeah.
Sorry.
So total energy, I'm just going to represent it by, okay, work done from, okay, I'm just going to say from 0 to 10. This was work done from 1 to 8, and this was work done from 8 to 10. So from 0 to 10, we just add work done from 1 to 8 plus work done from 8 to 10. Give me 21 joules, isn't it? Okay.
Yes.
So we're done with the first question. Okay, the second question requires you guys to integrate. So we're not going to do it because you've not done integration. Okay. So I'm going to jump to question number 3. Question number 3 goes, a block of mass M, which is equal to 5 kg, is released from a point A and slides on a frictionless track shown in Fig 3. Determine A, the speed of the block at points B and C. Part B of the question goes, the net work done by the gravitational force on the block as it moves from point A to point C. Okay. Okay, determine the speed of the block at points B. Okay, let's start with point B. let's go on point B, which is here. So the block is coming from point A to point B. It's going to lose some potential energy, and that potential energy is going to be converted into kinetic energy. You see? So we need to determine the kinetic energy for us to be able to determine the speed, isn't it? So it's frictionless, which means there's no loss in energy. This means that all the potential energy is going to be converted to kinetic energy, isn't it? Because there's no friction. Okay. So now, what is the formula for potential energy? Potential energy is mgh. Kinetic energy is half mv squared. Okay. So the mass is the same. We can cancel out the mass. Then we are left with gh is equal to half v squared. Okay. We're looking for v. So a v is equal to 2gh. Okay. The square root of 2gh. Now, what is this height? This height is the difference, okay, because we're dealing with point A and B, right? This is just for point A and B, okay? So height, this height is the change in distance between point A and point B. So we can substitute this h and write it as h A minus hb, okay? That's the h. So also similarly applies here. Okay, now let's substitute our values. We have 2 times 9.81 times the height difference, which is 5 minus 3.2. What is 5 minus 3.2? 1.8. So what do we get here? Are you guys getting 5.9 meters per second?
Yes, 5.9.
Yeah, 5.94 meters per second. Okay. Great. Now let's move on to part B. So there was an error here. I calculated for NB, it was supposed to be B and C, isn't it? The speed of the block at points. Oh, no, it's fine. This is the speed of the block at point B. Okay. Now I'm gonna find the speed of the block at point C. Okay. So this is fine. Now let's look at point C. We have some certain kinetic energy here, you see, at point B. So this is point B. Let's write the parameters at point B. The energy at point B, which is EB, I'm just going to call it EB, is equal to, because the ball is moving and also it is some potential energy relative to C, it is some potential energy, mg b minus C, okay? So it is some kinetic energy, which is, I'm just going to call it kinetic energy at B plus potential energy at B relative to C. Okay. So to find the kinetic energy at point C, we need to find this potential energy at B, because all the, okay, look at this, all the energy at B is going to be given to point C, okay? So energy at point C is equal to the kinetic energy at point C plus the potential energy at point C. Okay. All right. And let's calculate the total energy that we have at point B. Because this okay. So energy at B. Okay, this is a long way. Let me just take a short way here because it's kind of long. Okay, so we're taking point C as a reference point, as a datum line, which means the height is considered to be 0 here. Z is equals to 0. And then this is the height difference, okay? So B has got kinetic energy, okay? Kinetic energy at B is equal to half mv squared, is equal to half mv squared, okay? So if you substitute the kinetic energy that we have and the mass that we have, which is 5, 10, 9, we have no idea the breakdown. What are we getting here? I'm getting 14.75. Joules. This is the total kinetic energy that the mass possesses at point B, okay? So now to this kinetic energy, you're going to add another change in potential energy, which is given by the change in potential energy between points B and C, which is given by mg and hb minus hc. Okay, substitute our values. We have 5 times 9.81 times height at B, which is 3.2, minus height at C, which is 2. Okay, what do we get here? Cos, or okay, in cos.
As we're calculating kinetic energy, it's half mv squared equals to 5 times 5.9.
Oh, it's squared. Yeah, thank you very much.
Yeah.
What do we get then if we square that?
It's 87.025.
Oh yeah, 87. Thank you very much. It's 7.03. Okay, 87.03. Thank you, Joules. So this is the kinetic energy. Okay, now the potential energy. Let's calculate the potential energy at when the ball moves. The change in potential energy when the ball moves from B to C. So it's Okay, I'm getting 35.32 joules. What you're getting, Kosi?
Calculating.
Huh? You're still calculating. Oh, just
Calculating.
when you're done, please. Okay. So you see, all this energy is being converted to kinetic energy. So we should add it to the kinetic energy at point B so that we find the kinetic energy at point C. You see, the ball came with this kinetic energy, then it was at B, and then it gained also some kinetic energy when the ball when dropped down and lost some of its potential energy. So the potential energy was converted to kinetic energy. So now this is the change. So we're going to add that energy to 87.35. Okay. If I add, there's someone that is noise at the background. Yeah. Yes, I think you're on course again.
Yes. The change in potential energy.
Sorry?
The change in potential energy that you just calculated. I don't get 35.32.
You also got 35.32.
No, 58.86. I don't know if I'm wrong.
You got 58 here.
58. Yes.
Okay, this is 3.2, huh?
Yes, that's 3.2. This is 5 times 9.81.
Oh, it's 5, not 3. Okay, thank you.
Yes.
I'm using a mouse here, so I'm also failing to read my writing. Okay, okay, this is 5. Thank you. What are we getting here?
58.86.
Okay, 58.86. Okay. Now, the kinetic energy at C now, the total kinetic energy at C, we just add the kinetic energy at B, which is 87.35, plus this, which is 58.86. This will be a total kinetic energy at point C. What are we getting here? What are we getting? I'm getting 146.1. Okay, thank you. It's joules. Okay, don't forget the units, guys. Now, this kinetic energy will help us to find the velocity at point C, isn't it? Using the same formula here. Okay. So, okay, let me just clear out this area so that I find space to write. Okay. We know that kinetic energy is equal to, so kinetic energy at point C is equal to half mv squared, dv at C. Okay, so to find dv at C is just equal to the kinetic energy at point C by 2 over m. Then we find the square root, isn't it? What are we getting? We substitute all the values. Kinetic energy, it's 146.21 times 2 over the mass, which is 5. What are we getting here if we do this? $58.48. Sorry, okay, no. So just wait a second. Okay, we have about 10 minutes left. Oh, sorry, I'm getting 7.64.
7.65, yes.
Yeah, 65. Okay, meters per second. Right. So I think we have found the velocity at point C. Okay. Now let's continue again. Part B of the question: the net work done by gravitational force on the block as it moves from point A to C. So the net work done by the gravitational force is just, you remember, gravitational force is just the potential energy due to gravity. So the potential energy due to gravity is equal to, between points A and B, is equal to m g h a minus h c. Okay, so now we just substitute the values. The mass is 5 times 9.81 times the difference in height between point A and C, which is 5 minus 2. What do we get here? I'm getting 147.15.
1.5. Yes.
Joules. So this is the network done by the gravitational force on the block as it moves from point A to point C. Okay. Now let's continue. Okay, let's go to question number 5. Okay. Question number 4 requires some calculus that you haven't done, I think. Let's move on to question number 5. So number 5 goes like this: a block of mass 2 kg is attached to a spring of force constant K 500 Newton meters is shown in Fig 5. The block is put to a position x1 centimeters to the right of equilibrium and released from rest. Find the speed of the block as it passes through equilibrium. Okay, so just because we're running out of time, we have a block here, then I have an equilibrium position here, so I pulled it at distance 5 centimeters. They're asking us, if I release this block, what is the speed that it attain here when it reaches the equilibrium position? Okay, so we know that when I pull this object, it's going to gain some potential energy, elastic potential energy. Elastic potential energy, which is equivalent to, I'm going to call it elastic potential energy, EP, which is equal to a half kx. Is it kx squared or kx? Should be kx squared, isn't it? Okay, So now we're going to find the potential energy. Let's substitute half times the K constant, which is 500, times the distance of 5 centimeters, you need to divide it by 100, which gives us 0.05. What do we get here? Well, should be squared here. Okay. Okay, I'm getting 0.625 joules. Are you also getting that?
Yes.
Okay, perfect. So the first scenario, we don't have friction, you see? So it means when it gets to this position, when it has lost all its elastic potential energy, it means all the elastic potential energy has been converted to kinetic energy. There was no loss since there was no friction. So all the potential energy, elastic potential energy is converted to kinetic energy. So to find out kinetic energy is just, okay, the kinetic energy at that point is just equal to 0.625, okay, joules. So now they're asking us to find the speed of the block. So we know that from the equation of kinetic energy is equal to half mv squared. So making v subject, it's kinetic energy by 2 over m square root. Similar equation to the one that we used above. Okay, so now if we just substitute these values again, we get velocity. Let's substitute the values here. What is your kinetic energy? 0.625, okay? Times 2 over, what is the mass of the block? Are we given the mass of the block? Yeah, we're given.
Yes, 2.
Okay, yeah, now let's calculate. What do we get here?
0.79.
Okay, 0.79. Okay, let me just confirm that. Yeah, thank you. It's 0.79 meters per second. So that's the speed that this object to attain when it gets to the equilibrium position in the scenario where we don't have friction. Okay, so now when there's friction, now you see the horizontal surface is friction. It's part B. There's the coefficient of friction between the block is 0.350. So there's now a friction force. So friction force is given by normal force times mu, this one, times the coefficient of friction. So what is mu? Mu is just the normal force that is acting in this direction, okay? So it's, in this case, it's just mg, okay? Times 0.35. Mu is sort of like a reaction force from the surface going upwards. There's mg, so there's no movement in the y plane, so it's the same as mg. So we can find the friction force. Just be quick, we're left with about 1 minute. We can punch this in there, okay? So it's 2 by 9.81 times 0.35. What do you get?
6.87.
6.87. Okay, thank you. Newtons, right? Now let's find the energy lost due to friction. Energy lost due to friction, just the friction force times the distance traveled. In this case, which is 0.05, okay? Energy lost. Okay. What do we get here? I'm getting 0.3435 joules. So